Okay, so we're now going to do the last part of exercise 9.14. And here we are to show that the unrestricted deduction theorem is not sound. So when gamma is the empty set, when gamma essentially just isn't there, this isn't sound, and we want to provide instances of A and B such that B is satisfied by A, but A implies B is not tautology. So what this essentially is that given that A is, like, we've assumed A, or A is true, we can get B, so to speak, but that doesn't mean that A implies B is a tautology, if that makes sense. So, okay, so what we're going to do is we're going to pick an A and a B, and they're going to be the same as the second part of point 2. It's supposed to be point 2 of this exercise. So remember, in the second part we had that A was equal to the predicate P, unary predicate P, and B was equal to also the unary predicate P, but with the for all quantifier. So we can have that given this assumption that B is satisfied under A, because given any M, if M satisfies P of X, or A, so because A is P of X, for every V, then this is true. And remember, this is true because we have assumed that it's true, kind of here. For every assignment V every assignment V must be in the interpretation of P. So we're just going to say, yeah, it must be in P, because we have a free variable here, which means that any assignment V must map X to an element in P. But our interpretation V, it can map X to anything, really. There are as many different interpretations as there are elements in M, or that many different distinct interpretations. I mean assignments, as there are elements in M. So that means that each assignment is in M, which means that since each assignment is in M and each assignment is in P, it means that P under the structure M is just M. So essentially all the elements that exist in M are also in P. But if all the elements in M are also in P, then it means that this is true, because this is checking if all elements are in P. Yeah, and this last part just says this again. It holds if for every A in M, A is in PM, i.e. if P M equals M, which we just established was true because we have assumed that A is satisfied. It's valid. It's true. Okay, and here comes the second part. So we're going to look at why this, however, isn't necessarily so. However, it's not the case that for every M and V, it is we have that Px implies for all x Px is valid. So here we don't have, gamma is the empty set, so we don't have any assumptions. So we just need to sort of show that this is true for every M. And the way we show that this isn't true for everyone, M, is to have the same structure as last time. So remember last time we had M was, I think it was 5 and 5 and 6, and then we just let P under M that was just the set containing only 5, or was it 6? I can't remember. But anyway, so we have created this little interpretation here, which here. So P contains 5, and we have created structure M and the valuation V such that V of X is 5. So this first part here is true because X is mapped to 5 and 5 is in P. So this is true. But this last part here is 0, because this last part here is saying that for every x is in P, every element is in P, and that's just not true, because we have a 6 here, which is not, it's not in P. So we have found an example, so some interpretation for which this wasn't true, which means that it's not valid, essentially. So this was a bit confusing, but the main thing to take away from here is that pay attention that here we had that A without if the gamma isn't there, essentially, the A has been assumed, and if this A is satisfied under every M, it means that B is satisfied, because we have this for all x px. But this here, we have no assumptions of A being satisfied for all M. And because we have no assumptions for A being satisfied for all M, we can create some kind of an interpretation in which A is satisfied but B is not satisfied. Hence, the entire thing isn't satisfied. Yeah. So that's how we showed that the unrestricted deduction theorem is not sound.